Strangely enough, the touchscreen wasn't the very first gadget to use screen touches as input method. One of the devices to pioneer this principle was the so-called light pen. In the 60s of the last century, this remarkable gadget was widely used in design offices and studios. The tool relied on tracking the beam of the cathode ray tube, or CRT. Back in the day when LCDs did not even exist, only CRTs were used as image output devices. Besides the obvious difference in dimensions, the CRT employed a different principle of displaying the image. Flash screens consist of a huge array of tiny dots that light up to form a picture. The CRT, on the other hand, uses a beam that runs from left to right and from top to bottom at a speed imperceptible to the human eye. The trace left by the beam merges into a single picture and creates an illusion of a whole image on the screen. The process of moving the beam across the screen is called sweep. Strictly speaking, this movement is not entirely imperceptible, so all CRT televisions and monitors have a more or less noticeable flicker effect. Although human eye cannot follow the sweep, the deflection circuit that controls it always has accurate information on the coordinates of the beam. This is what the light pen, which is basically a standard photo sensor, relied on. When a user touched a certain point on the screen, the light pen controller would wait for the photo sensor to be engaged. Once it was, it meant that the beam was aligned with the pen. Then the controller would obtain the current beam coordinates from the horizontal and vertical deflection control units. If you happen to own a game console in the 90s, you probably remember that some games allowed to use a light gun. Its working principle was exactly the same. However, the light gun could shoot the TV screen from the distance. This, however, will not work if you use a console with a modern flat-screen TV. The reason is obvious. LCDs do not use beam sweeping, so it's impossible to determine the coordinates of a virtual bullet using this method. The light pen has a modern peer, the graphics tablet. While it's somewhat similar in appearance, in design this device has little in common. The development of the input device known as touchscreen also began in the 60s, and over several decades, more than a dozen types of devices have been developed. The first type of touch sensor that you might have been using every day is optical. Its principle of operation is based on light-ray intersection. The intercom panel that you're looking at now is actually a touchscreen. The device contains two sets of photosensors: vertical, to read the x-coordinate, and horizontal, to read the y-coordinate. The LEDs and photosensors are placed opposite each other. Initially, all LEDs are on, and the photosensors are engaged. Let's say the user presses button 4. In that case, these two rays will be cut. Thanks to this, the photosensors Y2 and X1 are no longer exposed to light. The keyboard controller reads this information and uses a lookup table to translate coordinates to corresponding button numbers. For example, Y2 and X3 correspond to 6, Y1 and X1 to 1, and Y4 and X1 to K, and so on. Once the keycode had been obtained, the controller passes the information onto the central unit for further processing. Why would an intercom panel use such a complex design, you might wonder? Why not use regular buttons with electrical contacts? Apparently, this makes the device more reliable and wear-resistant. The optical sensor has no moving parts. Also, it's quite easy to protect the LEDs and photocells from moisture by putting them under hermetic transparent covers. Ironically, such panels are not very reliable. On a sunny day, the photocells are exposed to sunlight, which sometimes causes them to malfunction. On the other hand, if an LED burns out, the panel functions properly during the day, but stops working once it gets dark. In this case, it displays the word error. Inhabitants of the building cannot make it to their homes. If you experience this, Here's what you can do. Use a flashlight to light up the keyboard if it's dark. Or, if you see the message at daytime, cover it from the sun with your hand. Sometimes it helps to clean the photocells and LEDs with a tissue. Another touchscreen type is probably also familiar to you. Remember the smartphones and tablets from mid-2000s? All of them came with this elegant plastic stylus. These devices used the so-called resistive touchscreen sensors. Contrary to popular belief, the touchscreen is not a thin elastic sticker. It's actually a piece of hard glass, or rather, two glasses glued together. A grid of transparent conductive material is applied to the inner surface of each of these glasses. Glasses are glued only along the perimeter. Their middle parts do not touch. The sides of each grid have leads that connect to the flex interface cable. So the cable contains only 4 wires, because the 2 grids are basically 2 resistors and have a total of 4 leads. This type of touchscreen can be easily checked with a multimeter. Since the glass is rectangular in shape, the resistance of the horizontal layer will be greater than the vertical one. Unless the user touches the surface of the screen, the layers have no electrical contact with each other. So, what happens when the user presses on the touchscreen? The top glass deforms, and the 2 grids come into contact at the point of touch. In this case, a circuit is established between the horizontal and vertical grid resistors, which can also be observed with the help of a multimeter. Obviously, the resistance of the segment between the touch point and the edge of the screen will depend on the distance between them. The shorter the distance, the lower the resistance. The longer the distance, the greater the resistance. The touchscreen schematic diagram can be represented as a number of resistors connected in series and in parallel. Let's say the resistance of one resistor is 100 ohms. While the device is at rest, there is no electrical contact between the red and green grids. Imagine that the touch occurs at this point. Let's call it T. In this case, the resistors along the y-axis turn into a divider, the lower arm of which consists of 4 resistors with a total resistance of 400 ohms, and the upper arm is 100 ohms. And if power is applied to points Y2 and Y1, for example 5 volts, the voltage at point T will be exactly 4 volts relative to Y2. It can be measured using either of contacts X1 or X2. Since the current consumption of the voltmeter is negligible, the current flowing through the horizontal resistors can also be neglected, and there will be no voltage drop across them according to Ohm's law. So the potential at points X1, X2 will be equal to the potential at point T, and will amount to 4 volts relative to node Y2. To read the horizontal coordinate, we perform a similar action, but voltage is applied to nodes X1 and X2, and a divider is comprised of horizontal resistors. In our case, the left arm resistance will be 500 ohms, the right arm 200 ohms. If the voltage applied is 7 volts, for example, the voltage at T point relative to X1 will be exactly 5 volts. To measure it, accordingly, we must use node Y1 or Y2 relative to X1. When touchscreen events are processed by the CPU, this operation takes milliseconds and is of course fully automated. Yet, the coordinates X and Y are read in turn, just like in our experiment, because there is no other way of doing it. Resistive touchscreens were common in devices that ran Windows Mobile OS. Although it's obsolete by now, you can still find gadgets that use them. Most car nav systems and dashcams have them because they run under Windows CE. If you own one of these devices, chances are it has a resistive touchscreen. Another obvious sign of this is the presence of a plastic stylus that cannot work with modern touchscreens. It's important to note that all resistive touchscreens available for purchase have common electric design, which means if you're up to replacing one in your device, all you have to look at is dimensions. There's a little nuance though. The flex cable connector, although always 4-pin, may be different in size and pitch. If this is the case, you can always solder it. And it can be positioned differently too, then you're gonna have to use jump wires. I used to replace these parts in my shop a while ago using a low-power soldering iron and a little bit of experience. If there are more pins on the flex cable, or it has a chip, then it isn't a resistive touchscreen. Because touchscreens are manufactured with varying parameters, after replacing the part, calibration is always necessary. The calibration routine can usually be activated with Devices menu and does not present any difficulty. Hypothetically, any gadget that has a screen and a mouse can be equipped with a resistive touchscreen. You can put it on a regular PC monitor and your car radio screen in case you're using it with an external Android-based media player. You can order a touchscreen bundled with a controller that can be connected directly to a USB host. I will leave some links to order it in the description. We are all used to zooming pictures with a certain touch gesture that everyone knows. This function is called multi-touch. Unfortunately, a resistive sensor cannot process touches at several points. A multiple touch on a resistive touchscreen will yield an average voltage value, which will not correctly translate to any actual coordinate. There were attempts to design resistive multi-touch screens, but they never saw mass application. Another obvious disadvantage of a resistive touchscreen is its low accuracy. For example, if you've lost your stylus, it's almost impossible to use an on-screen keyboard with your fingers. Finally, resistive touchscreens were replaced by capacitative touchscreens. This is exactly the type of sensor that is widely used today in smartphones and tablets. As you might guess, it uses capacitive sensors that respond to changes in the amount of charge at the point of contact. Before we look at how a capacitive sensor works, let's briefly recall what a capacitor is. A capacitor is a device capable of accumulating charge and storing the energy of an electric field. The capacitor consists of two electrically conductive plates and an insulator located between them. In the initial state, the plates are charged neutrally. When a power source is connected, charges opposite in sign form on the plates. If the power is turned off, the capacitor will store some of the energy inside, and when the load is connected, we'll be able to power it. In theory, the capacitor could well play the role of a rechargeable battery, but unfortunately, the amount of energy modern capacitors can store is too small for this application. The capacitive touchscreen is also a capacitor. The insulator is the glass of the smartphone. The lower plate is the transparent conductive layer applied to the glass from the inside. The upper plate is the human finger. The human body, like any conductor, has a certain initial electrical potential, but for simplicity, let's imagine that is grounded, since this is not important in terms of the algorithm. The touchscreen controller applies a small voltage to the bottom plate of this makeshift capacitor. Let's call it T. As a result, a certain amount of charged particles collect there. That is, the capacitor is charged. After that, the controller removes voltage from point T and connects it to its internal reference capacitor C, the capacity of which is known. From the physics class, we know that the voltage on the capacitor plates is directly proportional to the amount of charge and inversely proportional to the capacitance. When two capacitors are connected in parallel, their capacitance adds up, so the charge from the touchscreen plates partially flows into capacitor C. As a result, the voltage at point T decreases. So the touchscreen controller can detect a touch by monitoring the change in voltage of point T, since the capacitance depends on the distance between the glass and the finger. Charging and measurement cycles alternate at a frequency of approximately 180 Hz. As a result, the controller receives information about the state of the touch panel dynamically. Since the task of the touchscreen is to determine the coordinates of a touch, and not just the event is, There is a large amount of T-points on the sensor surface, which are usually organized in the form of a matrix. Matrix connection is used to reduce the number of control wires needed to scan the entire sensor surface. To get a better understanding of how such circuits work, you can check out my video on implementing dynamic display using Arduino. So instead of reading the potential of each point individually, the controller measures capacitance of an entire row and column. Once the voltage has changed, for example in column 4 and row D, it figures the touch happened at D4 point. Rows and columns in this configuration duplicate each other because there are two capacitors at each touch point. The obvious disadvantage of this setup is absence of multi-touch functionality. Let's say we simultaneously touch the glass at points F7 and C3. The controller will detect change of voltage on lines F, C, 7 and 3. But it won't be able to differentiate though between this situation and touching of points F3 and C7, because the voltage map is the same in these two cases. This happens because this type of touchscreen sensors use a human finger as a capacitor plate. Such sensors are called surface sensors or self-capacitance touch sensors. The touchscreens operating on the newer projected capacitative touch technology are completely free of these limitations. They also use the matrix setup, but unlike surface sensors, both plates are placed onto the glass, and the intersections of rows and columns form capacitors. Their number directly affects the resolution of the touchscreen, and inexpensive models can reach several thousand. The human finger in this setup does not serve a capacitor plate. It only affects the capacitance of the capacitors. The technology is called projected because the charges move outside the glass. Such touchscreens can read finger gestures even at a small distance. The main advantage of projected sensors is that the controller here can charge rows and columns individually, while in surface sensors, all locations have the same initial charge. Let's say the user touches the screen at points B7 and G3. Their doubles are located at points B3 and G7. But at the time of scanning of B7, the charge is only present at row B and column 7, which means points G7 and B3 cannot affect the result. Same thing happens when scanning point G3. So individual charge control of rows and columns allows projected touchscreens to implement the multi-touch function. Due to the high resolution of the matrix and the complex algorithm of operation, projected touchscreens have a large number of pins and therefore require a more complex control circuitry than surface touchscreens. Sometimes the controller is located on the mainboard of the smartphone, and sometimes it is installed on the flex cable of the touchscreen. Apart from multi-touch function, projected sensors can also measure applied force, which makes it possible to implement even more complex gestures, without which no modern mobile phone can exist. Capacitive touchscreens at the same time have one practical disadvantage that I think many smartphone owners have been confronted with at least once in their lifetime. No, I'm not talking about winter use and gloves. I mean service life. After a drop, the LCD display often continues to work, but it turns out that replacing the touch sensor as a separate part is problematic. Capacitive touchscreens are most often supplied glued to the LCDs. It's called a module, and in some models, they are even glued over the entire area. To mount such a sensor, a special transparent glue is used, which can only be properly applied at the factory. Hypothetically, you can replace the touchscreen sensor in any phone, but the mobile repair people are usually very reluctant to do it, and in most cases, they would tell the client that the part is only replaced as a module assembled with the LCD, which in fact is not entirely true. Capacitive touchscreens cannot boast of interchangeability either. Only a specific part is suitable for a specific device model, which can cause you to spend some buck. If we're talking about a less-known manufacturer, the device with a broken glass often ends up in the trash can. So when purchasing a new smartphone, what you have to do right away is buy and install a soft protective case or bumper on it.
Theories are products of thought designed to facilitate understanding, not to inform practice.
Whatever that means, we have made it to the practical part of the video. So sit back, the fun is just beginning. Today, we're going to connect a resistive touchscreen to our beloved Arduino. Like I said, resistive touch sensors usually have a standard connector in the form of a flex cable with a standard dip 2.5 mm pitch. You can solder it, but I do not recommend it because the bottom of the flex is very thin, so chances are you're just gonna make a large hole in it with your iron. So, to connect the touchscreen, we're going to use this little socket. You can find it in most old-school CD-ROMs. We will wire the touchscreen directly to analog lines of Arduino. Our task is to alternately supply power to the horizontal and vertical resistive grids and read the value of the coordinate from a perpendicular plane. Arduino analog lines can also work in digital mode, so the same processor pins will alternately serve as inputs and outputs. The resistance of the touchscreen matrix typically ranges from 200 to 800 ohms and is chosen so that the measurements are relatively accurate at a supply of 5 volts. Here's our schematic diagram. The sensor will be wired to lines A0, A1, A2, and A3. The flex cable can be inserted both ways. You can turn it 180 degrees and it'll still work, but the X and Y coordinates will be flipped. Let us first try to read the X coordinate. To do this, we need to set the mode of lines X1 and X2 to output and lines Y1 and Y2 to input. We will use the pin mode operator to do it. If you're not familiar with Arduino programming, I have a great video for newbies on that. The link you may find in the description. Okay, so X1 and X2 will serve as outputs and Y1 and Y2 as inputs. Now we have to apply 5 volts to the horizontal grid, which is located between leads X1 and X2. To do it, we use these operators: digital write X1 low and digital write X2 high. Set X1 to logic 0, set X2 to logic 1. Let's run our sketch. We can see the levels are set. The standard power supply of Arduino is 5 volts, but at the moment it's powered from USB, which is a bit weaker, so the actual voltage is lower here. Now, pressing different points on the sensor surface, we should be able to see change of voltage on leads Y1 and Y2. Indeed, it's changing. But it looks like we are reading the Y coordinate and not the X. Let us flip the connector. Now X1 and X2 are correctly attached to the horizontal grid, but the voltage is inversely proportional to the coordinate. Let us switch the levels on leads at X1 and X2. Check it out. Now it looks like everything's working as intended. Let us now read the voltage on lines Y1 and Y2 using Arduino's analog-to-digital converter and use a special debugging operator serial to display them as a graph on the computer. Serial uses USB port of Arduino to transfer data to your PC. In the setup section, we must specify port speed. It'll be 9600. Then in the main loop, we read the value of line Y1 and store it in the K variable. Then, using the serial print line operator, we send it to USB port to be plotted on computer screen. We should also add a delay command here, specifying duration in parentheses. This is necessary so that the data received from the ADC does not overflow the virtual USB channel. Running the sketch. Arduino's AD converter has 10-bit resolution and can output values from 0 to 1023. As more data is received, the graph is automatically scaled. Let's try to get it to display some sort of a sign. If I draw a circle on the panel, it should yield a sign. Just to mind you, the graph shows only x-coordinate for now. You should remember from the calculus class that the coordinates of points lying on a circle are in fact sine waves, which we have just proved by doing our mini-lab. A problem can be seen on the graph though. When the user picks up the finger, the horizontal and vertical grids are no longer in contact. As a result, the lines Y1 and Y2 are floating. The analog-to-digital converter reads noise in this case, which can be erroneously interpreted as good data by the program we're going to write. To prevent this, we have to use resistors to pull the input lines either to ground or to positive power rail. The value of these resistors must be proportionally large, so that they do not affect the measurement. Fortunately, the Atmega 328 already contains built-in pull-up resistors, and all we have to do is activate them programmatically using the input pull-up parameter. As we can see, the graph now looks tidy. The released finger state now corresponds to the maximum value of the ADC, that is 1023. The touch sensor is usually designed so that the maximum coordinate it can produce will be less than this value. Let's try to read both coordinates now. The procedure is basically the same for the y coordinate, it's just that x and y will now alternate, and we are going to have two graphs. The serial operator allows that if you use a comma. Let's check it out. And we have another problem. The program works, but the output data contains errors. This is likely because we start reading too soon after reprogramming inputs to outputs and vice versa. Let us add delay operators after changing data line modes, as well as measuring the ADC data at the inputs. Now it's working as intended. Using this touch screen, we can control virtually anything, provided it's connected to Arduino. So let's put this thing to practical use. Today we're going to build a mini piano. I will print the musical keyboard on a sheet of paper and put it under the touch screen. Next, we will place the coordinates corresponding to each key into a table and write a program that will, based on this, play the desired note. Here's what I've come up with so far. We got a new SPK variable in our definition section. It's responsible for addressing the speaker and contains its data line number. We also got three arrays: whites, blacks, and tones. The whites array contains x coordinates of white keys, the black keys. The tones array has note frequency in hertz. Basically, x coordinates of white and black keys are different anyway, but I've decided to put them in separate arrays to improve key recognition quality. We'll talk about that a bit later. Parts of the program responsible for reading touchscreen data have not been changed, except I decreased the delay to 5 milliseconds, because 25 milliseconds presented a noticeable lag during playing. I wanted node duration to depend on the duration of the key being played, just like in a real instrument. So to play the sound, I used the tone command, which can play the meander of the specified frequency regardless of the operation of the main program, and the sound continues until the note on command has been received. So the first thing we do here is compare the x coordinate to 1000. When no key is played, its value is around 1018. That's why I chose 1000. If x is less than this value, then a key was pressed, so this block is executed. What we do next is compare the y coordinate to 500 to find out whether white or black key was pressed. Based on that, we use either the white keys array or the black keys array. The loop goes through all array values while the current x coordinate is greater than the value obtained from the array. If this condition is false, it means we found the coordinate of the note we want, and the I variable, which is incremented while the array is scanned, contains its ordinal number. All that's left to do now is query the tones array and pick the note frequency value. Then we play it through the speaker using the tone command. Shall we try? Pretty good, huh? How about... If you'd like to build a touchscreen-based digital piano of your own, the links to order Arduino Uno and the touchscreen glass you may find in the description. And that would be it for today. If you like this video, please don't forget to comment, share, and subscribe. And if you wish to drop me some Bitcoin or Ether, please use wallet numbers you may find in the description. This was Ramatina. Be good.